Okay, so first thing is today I put up some kind of lecture slides calling this week 16. I'll go through and rename these. It's all going to be, all these are linear regression, and I'll kind of name them to be a little more specific about what we had talked about in each one of these. Today, we're kind of using the week 16 slides. I also put up, we were working with this last, before the Thanksgiving break, with this GPA data, and we're also going to use this traffic data one today as well. Okay. I also put up on kind of the general, just under kind of the general files tab, there's this figure out your grade tool, or figure out your grade. So let's download this, see what it looks like. Oh, I already had it open, so it doesn't matter, we can see what it looks like. So on Canvas, you can kind of see the different categories that are weighted differently to kind of give you your grades. So you've got what your Excel grade was kind of across all the assignments, your average kind of iClicker grade, Connect grade, and LearnSmart. So whatever you have, you would put your scores in here. So, maybe you had 100 on the LearnSmarts, 90 on the Connect, Connect grade was 90, iClicker grade was 90, Excel was 80. You can get that information from Canvas. Here, so let me go, so I don't show anyone's grade. Let's go to Student View. Let's go to Grades. So if you scroll down here to kind of the different categories, the only categories that were kind of weighted, we have your online quiz score, your Connect assignment score, your Connect grade, your LearnSmart assignment score, and then your Excel. So these, I'll kind of move this around so that they'll all be next to each other, but here would be, I don't have any because this is a test student, but whatever your kind of online quiz percent is, your LearnSmart, your Connect, your Excel, and then you'll have all the information you need to kind of enter in these four. You would then put your first exam score and your second exam score. Right. And then you can really play around with this final one. So obviously we haven't taken the final yet, but you could say, what if I did really, really bad and I bombed the final, I got 25? Well, this hypothetical person would still end up with almost a C-, right? So maybe even if you bomb and get a 30, you'd still end up with a C-. Let's say you do really well, could end up pushing over to a B, kind of despite having this kind of previous bad exam. But you notice if we leave this out, we're going to see kind of where we stand. But that's kind of treating these as my best two exams, which they might not be, right? So you can play around with that hypothetical kind of final grade to kind of see for different scores, what would your potential grade, kind of final grade be in the class. Now, obviously, we still have that fourth Connect and Excel assignment that are due at the end of this week. I'll actually post another Excel and Connect assignment that'll be due at the end of next Friday. Now, when I post these, right, I drop the lowest of each type of Connect, Excel, and LearnSmart, right? So if you've done the previous 4 Connect assignments and you're happy with your grade, if you don't do the 5th one, it would be a 0 and it would just get dropped. Same thing with the Excel. If you've done the first 4, you don't have to do the 5th one because if you don't do it, it's a 0 that gets dropped. Now, if you don't do it, but you had done really bad in one of the Excels, well, now, the 0 gets dropped and one of the bad Excel grades counts. So it's kind of there for you if you want to help improve kind of your Connect or Excel grade. But if you're happy with, what you think you did in the first 4, then you can kind of, you don't have to do that 5th one because it would just get dropped. Right? Also, I won't lie, I think that especially the Excel, well, probably both the Excel and the Connect assignment will be pretty easy, that 5th one. So, if you're kind of trying to boost your grade or you're thinking about choosing between doing the 4th or the 5th one, I would probably kind of lean towards the 5th one. It'll be quite a bit easier. So I'll get those posted today. If you have any questions about any of that or kind of how to use this, figure out your grade tool, please let me know. I just think it's kind of nice to think about. You've got several classes, how much time you need to kind of put in studying for a final or something, So it's kind of a nice little tool there. Okay. Any questions on that before we keep moving? Oops. All right, so let's go here. So we kind of left off last class. We had this idea that we could include not just one kind of variable on that right-hand side, we include several of them. We're still trying to minimize the sum of the squared errors, or how, or kind of our line of best fit. Now, it's easier to think about a line of best fit when we only had one variable. It's, you know, this 3, then 4, 5-dimensional as we start adding more variables in thing. They can't really visualize, but we're still trying to kind of find this line of best fit across all these different variables. So there's a solution to doing this. You know, we would have take a derivative in respect to this equation for each one of these coefficients and equations and unknowns. We could solve for it. Never going to make you do that. We don't really care as much about the computation for the sake of what we're doing in this class. But what I do want to focus on is the interpretation, right? So the interpretation is still a 1-unit change in our x variable would cause whatever that estimated coefficient or that slope coefficient we get is, we predict that change in the y variable holding every other variable that we put in that regression constant. So we take a look just as a reminder at that GPA data that we were working with last class, right? So we had some of this information on students, their GPA, and some other stuff. So if we just run simply like a simple linear regression where we have a GPA and athlete, we did that last class. Well, a 1-unit change in athlete is, it's a 1-0 variable, it's going from being a non-athlete to being an athlete. So relative to a non-athlete, a student athlete, we would expect a predicted GPA of about 0.28 lower. We also said when we see these e to the negatives, that means move the decimal point 9 places to the left. So this p-value is pretty much 0. Right? So the p-value of pretty much 0, we're going to be able to reject the null. So just kind of a reminder in all of these regressions, our null hypothesis is always that slope coefficient is equal to 0. So if I get a p-value that's low enough, I can then reject this, which if I'm rejecting the null here, I'm saying I'm rejecting that there's no relationship between GPA and a student athlete, or that x and the y variable. Or another way of saying I found significant evidence that there is a relationship, right? That it's something other than 0. Okay? So we had that. We then said, well, look, I mean, there's a lot of other things that are probably better at, or probably more important when predicting GPA. So we ran the same regression, but we included all these additional control variables. So now when we're interpreting something like this athlete variable, it's the effect of being an athlete relative to not on your GPA. And because we've been controlled for all these other important control variables, the sign of that coefficient has changed. Right? And we'll talk about a little bit more of the omitted variables here in just a second. But I also kind of want to point out when we have all these additional x, right hand side control, independent variables, those are all, you know, different ways of saying the same thing. Now the interpretation is, okay, hypothetical 2 people, they have the same SAT score. They have the same score on this verbal math test they took. They're both either female or they're both male. They're kind of both the same kind of, you know, race. Same number of total credit hours. They both went to this high school the same size. They ranked the same place in their high school. And here, I won't mention too much on this. I just squared the SAT score variable. It's just some additional information we had. So all those things are identical. But one of them is a student athlete, one of them is not. The change in the predicted GPA would be about 0.13. Right? So when we have a lot of these other conditional control variables, the statements that we're making are a lot more powerful because we're comparing more apples to apples. Right? Whereas if I just had the athlete variable in here, I don't know, just saying something to the student athlete, not controlling for all those other things. Well, I mean, what if the student athletes happen to have a lower or a higher SAT score or kind of intellectual ability? I mean, then this is really not telling me much. But when I can control for all these other factors, now that carries a little bit more weight. Okay. Now, one statistic, it gives us a lot of this, these other statistics that we haven't really focused on. I think up to this point, really, we've talked about the coefficients. We can get the test statistic by dividing the coefficient by the standard error. And then also we pay attention to the p-values. Right here, anytime I see an e to the negative, I really can think of those as essentially p-values of 0, right? I mean, once I move the, right, this one was what? E to the 89, so move the decimal 89 places to the left, this is essentially 0. And then I can think about anything with a low p-value, these are all going to be less than an alpha of 0.01. So with the 1% significance or 99% confidence, I could reject the null here. Which remember, that null was that these slope coefficients were equal to 0. So I'm rejecting that. I found significant evidence that there's something other than 0. Now notice for some of the variables I didn't, right? For the white kind of identifier, that p-value is 0.92, so it's not even close to significant. Right? But I could go through every single one of these variables and determine if they're significant at certain levels. Okay? Just by kind of that same rule. Is the p-value, oops, less than alpha. Okay. So that was kind of some stuff we talked about last class, just kind of a little bit of a reminder of some things. But one thing we didn't really spend time on is talking about this R squared. Okay? So R squared is a measure of how, I'll say this a couple different ways, and maybe it's just good ways to think about it. It's some measure of how accurate our predictions would be. If we used our linear regression, right, to make predictions, excuse me. So when we're making predictions with whatever regression model we've used on, all right, so we've got whatever those estimates we get from Excel are for the coefficient on the intercept and the slope. Here's the, we could use those values and plug in different values for X to come up with predicted Ys. Right? Now, we can observe the actual Ys, like if we look at that data set, we can see the actual GPAs, and we could predict for any one person what that GPA would be, and we would probably be close, right? Our line of best fit, we've minimized the errors we've made, but we're still gonna have a little bit of error, right? So basically, how well we're doing with our predictions is gonna depend on kind of what those error terms are, right? And if I don't include as many variables on the right-hand side there, it's likely that those errors are gonna be larger. So I can think about it as, it's really this ratio of, if I look at my predictions, the deviations from kind of the average Y, so this numerator is a measure of how much of the variation am I explaining with my prediction, and then the denominator is just how much variation exists in that Y variable, right? Kind of almost looks like a measure of variance here. So the ratio of those two, it's like, how much am I explaining out of the total variation that exists? So an R squared, right? Anytime we see the output from Excel, it's going to be between 0 and 1. So it kind of represents the proportion of that Y variable we're explaining with whatever X variables, right-hand side variables we've included in our regression. Now, usually we can think about this as a percent as well. If the output, where is this? Yeah. If the output here for our R squared is 0.29, that means the proportion of the variation we're explaining of the variation that we see in GPA with all of our control variables is about 0.3, or we explain about 30% of the variation in GPA with these control variables. Now, obviously, when we want to get the R squared as close to 1 as possible, because if we can get it up to 1, that's 100% of the variation, that means we can make perfectly accurate predictions, right? There's essentially would be no error terms there. Now, we can get close to that 1, but in practice, unlikely we'll ever get exactly to an R squared of 1, but we like to see R squareds that are higher, right? Because here, what this is telling us is that there's still 70% of the variation that exists in GPA that I can't account for using my regression model. So there's still a lot of other things that matter, right? And if I don't include things that matter, oh, I keep doing that. If I don't include the things that matter, right, I'm going to end up with this, what we call omitted variable problem, right, or this omitted variable bias. So I think we mentioned a little bit before the break this example where if I'm trying to estimate the effect of police expenditures, how much I'm spending on my police force, on crime rates, right? Well, I might find that this is positive. Well, does that really mean that spending more on my police force will increase crime? Well, remember, we have to kind of stop and pause. Remember, this is not, we should not be making these causal interpretations, or we should be cautious about making them causal. They're really just evidence of a correlation. And if I haven't included a lot of other important variables to control for, like police force expenditures, areas that are spending more on their police force are probably just likely to have maybe a higher proportion of lower income individuals, which I'm not accounting for at all. I mean, I've looked at the unemployment rate, but I haven't control for kind of the income of whatever state or county or whatever level I'm looking at this is. And so it's not just going to pick up the effect of the police force expenditures, it's picking up the effect of anything else that's related to having to spend more money on my police force and also related to crime. And there could be a lot of other things. I mentioned income as one. Right? There's probably several other things. Another, I think an interesting example is if we go back to that birth weight data, right? And I look at different birth weights and whether the mother smoked while pregnant or not. So 0 if she didn't smoke, 1 if she did. So now the interpretation of B here, this slope coefficient would be a 1 unit increase in X. Well, if X is either a 0 or 1, it would be going from not smoking while pregnant to smoking while pregnant, would predict that birth weights would go down by whatever B is. So I run this regression, I definitely find a negative value here. But does that really mean smoking while pregnant is causing lower birth weights? Well, it still could be that it could cause lower birth weights, but it's probably also capturing the effects of a lot of other things. If we look at the data, we'll also find that lower income mothers and mothers with lower education levels tend to be more likely to smoke while pregnant, and having a lower income or lower education level is also, you usually aren't aware, or you don't have the funds or the means to provide as much prenatal care or buy the kind of higher quality foods or go to the regularly scheduled visits as often. So I'm not just going to be picking up the effect of whether or not smoking while pregnant decreases birth weights, but also the effects of having lower income, the effects of having a lower education. And so, if I don't have any other additional control variables here, I'm probably going to end up with a coefficient that's much larger, right, than what it actually needs to be, because it's capturing more than just smoking while pregnant. Okay. And I think I went through this example at the end of last class as well, where I could do the same thing, autism and organic food sales. I mean, this is a perfect correlation. I don't think anyone's trying to argue that organic food sales are causing autism. It's likely that there's an outside factor, another variable we're not accounting for, like an increased interest in health, higher income levels, so we can have more money to kind of make sure that we're eating higher quality foods, but also more concerned about our health and maybe more money in the healthcare system. We're better able to identify autism, right? So it's not that these two things are causal; they just happen to be correlated with a variable that's outside that's causing both of them that we haven't included in this discussion, in this picture. So you can go through the mathematical proof, and basically, whenever I come up with an estimate for, say here, B1, so that's the relationship between X1 and Y, that estimate will include the true relationship between those variables, but also this additional bias component, right? And this bias component exists if you've got the variable that you've included, X1, is correlated with any other variable that you've left out of your regression, and that variable that you left out would have had an effect on Y. And this is almost always applies, right? You can probably always think, no matter what example we're looking at, we probably never truly capture every other variable that's important. So our estimates will always, if we're just using this multiple linear regression, have some level of bias. But as we add in additional control variables, notice here, if I added X2 into this regression, well, I've now eliminated this bias component. Now, there might be a third variable, X3, that I didn't eliminate that by, but as I add in more and more X variables here, or right-hand side variables, I can eliminate a lot of these biases that would exist in my slope coefficient, or for B. Okay. So I know last class we looked at kind of the athlete and SAT score example where, once I included the SAT score and once I included even more controls, we saw that this coefficient was greatly affected. So we want to be careful, this difference between causation and correlation. Before we go to Excel here real quick, I always like this. I used to think, so why does correlation not imply causation? Well, Y could be causing X as opposed to X causing Y. It also could be that some outside variable Z, or I was calling it X2 in that previous slide, doesn't matter what we call it, some other variable, could be causing both X and Y, and Z isn't in the regression. So kind of little sketch here. I used to think correlation implied causation. Then I took a statistics class, and now I don't. Sounds like the class helped. Well, maybe, right? Because maybe it wasn't taking the class that caused this understanding. Maybe it was some outside variable Z that made it more likely I took the class, but also more likely I could understand the difference, right? So let's go here and go to Excel now. So we've got this idea of omitted variable bias. We kind of, hopefully, we'll see some of that pop up here. But I did want to just kind of use this traffic data file because I think this is a really interesting example of what we can do with linear regression. It gives us a little bit more interpretation. It also is going to let us look at a variable that our Y variable is now going to be either 0 or 1. And the interpretation will be a little bit different now. Very similar, but a little bit different. Okay? So let's say I have this data set, right? I've got all, these are traffic stops in, how did I want to download this. It was a large, diverse city in southeastern Texas, which I assume is Houston. So it had the original data set was much larger. I think here I've got 22,000 observations, right? But I kind of only took here's the identifier. So originally it had a bunch, I think it was like 70 or 80,000 observations, but I only took out traffic stops that the reason why they were kind of pulled over was speeding, right? And I could have done some more with the original data. Maybe we will even more so the rest of this week, but I'm only looking at traffic stops where the reason for the stop was speeding. And then I have things like whether or not a ticket was issued, whether or not arrest occurred, the officer's years of service, driver's age, and I've got some kind of racial kind of identifiers here. I've got a gender identifier for 1 if the driver was male, 0 if not. So the first regression I want to run, before we run that regression, we have to add in that data analysis tool. Okay, so if you're not on a Mac, it's Files, Options, go to Add-ins. And even on some Macs, I think you can access it this way as well. Go to Manage the Add-ins and make sure that this analysis tool pack has a check mark next to it. Now when you go to your data tab, it's going to be over here. I would try to get this. This is what you'll kind of be using on that 5th Excel assignment I post today. I would try to get this added into your Excel as early as possible. If you're having any issues with it, please let me know. Like I said, some of the Macs are a little bit different. If the Mac's old enough, you need to use something called Stat Plus LE. It's a free program you can download. I know a lot of you also can access it through your Tools tab, and then there should be like an add-ins or manage add-ins, and you kind of click the analysis tool pack. But I know on some Macs it's a little bit different. So if you're having issues finding that, please reach out to me, email me. I can help you, kind of troubleshoot and get that added in. Also, if you are on just a non-Mac and this isn't working for whatever reason, I've had a couple. Sometimes it's just restarting your computer after you select it. So please try to figure that out and reach out to me if you're having any issues with it. Okay. So now that we have that in there under the Data tab, I'm going to go to Data Analysis. I'm going to scroll down to Regression, hit OK. So what I want to do is look at whether or not receiving a ticket changes depending on the driver's age, officer's years of service, and whether or not the driver's male. So I'm going to select this ticket variable, right? So did the driver get a ticket or not? So Control Shift or Command Shift on a Mac down arrow. The X variables I want to include whether the driver is male. So I'm going to select that column. But then I'm also going to try to select whether or not, the driver's age and officer's years of service. So it looks like I've selected those 3 variables, right? And I want to run this regression. I selected the labels. I'm going to put this on a new worksheet. I'm good to go. I hit OK. Gives me an error, okay? So the problem is, and I'll cancel to get out of this, is if I try to run a regression in Excel, the variables I put on the right-hand side all need to be next to each other. So generally, I would say the best kind of way to do this is, so I held Control-Shift and just copied all of my data. I'm going to put it on a new sheet, and then I'm, have the original one. I'll call this kind of maybe my raw data, so I don't ever want to delete my original data, my raw data. But here on this worksheet, I don't want to use these kind of race identifiers, at least not yet. I just want is the driver male, the driver's age, and the officer's years of service. So now they're all next to each other. I go to data analysis, hit regression. The Y variable I want is ticket, so I select that. Control-Shift down arrow, or Command-Shift on a Mac and the down arrow. I want these three variables, so I'll select those three variables as my X variables. I selected the labels, which are just kind of the labels at the top, put it on a new worksheet, hit OK. Now it runs without a problem, right? So that error, when it says like contiguous or whatever, non-contiguous cells, that's just, it's just making sure that the variables you want to include on that right-hand side, your X variables, are all right next to each other. So we'll do a little bit of interpretation of our results here, all right? So remember, it's a 1 unit increase in the X variable causes the predicted Y variable to go up or down by whatever the coefficient is. Well, here, our Y variable, was 1, 0. So 1 if you got a ticket, 0 if you didn't. So if I'm trying to predict Y, right, increases in Y are like changes in the probability that I get a ticket, right? If that predicted Y value goes up, it means I'm more likely to get a ticket. It's more likely that that ticket variable is 1. And if I don't, it's more likely I'm getting a 0. So the way I could interpret these results are a 1 unit increase in kind of service of the officer is changing the predicted probability of getting a ticket by 0.002. So the longer an officer is on the force, the more likely they are when they pull someone over for speeding to write a ticket. Okay. We would interpret the driver's age as one more, kind of as a driver gets 1 year older, if they get pulled over for speeding, they're what, 0.003 or 0.004, so 4% less likely to get a ticket, which kind of makes sense, right? You do a lot of dumb things when you're a young driver that make it more likely you might get a ticket once you're pulled over. Officers years of service, that one, maybe they just become a little bit more, I don't know, harsher as they are on the force longer. Now this driver male variable, remember that was a 1 if the driver was a male, 0 if not. So 1 unit change in our X variable now is if the driver goes from being kind of female to male, so a male relative to a female, if they get pulled over speeding, they're about 0.009 or 0.9% less likely to get a ticket. Now, that's the interpretation of our coefficients. But remember, we start out always assuming, right, that null hypothesis was that the slopes are equal to 0. So I might find a value other than 0, but if it's not far enough away from 0, I'm not going to be able to reject that null hypothesis, which is that there's no relationship. Okay? So here, these e to the negatives, remember we said these are essentially 0. So p-values of 0, well, that's definitely going to be less than 0.01, 0.05, and 0.1. So at all levels, I can reject the null, but there's no relationship between driver's age and getting a ticket and officer's years of service and getting a ticket. But for whether or not the driver's male, it's impacted whether or not. So might have to cut this out. So we have a p-value of 0.16. That's okay. So the effect of being kind of the driver's male, we can't say it has a significant effect on whether or not someone receives a ticket because that p-value isn't less than any of our alphas, right? It's not less than 0.1, it's not less than 0.05, and it's definitely not less than 0.01. Okay? So we can make the interpretations, but also we have to remember, is it significant? And here, your gender is not, or it doesn't have a significant impact. So that's pretty interesting. So I want to push this data a little bit further. So we'll go back to the raw data, right? And now I'm going to include those same variables, but I'm also going to look at whether or not the officer was white, whether or not the driver was white, right? And then whether or not the officer is white and the driver is non-white. Okay. So actually, I might switch this around here. So I actually I'm going to actually do driver non-white, which is just equal to let me see if I can do this real quick. I think in my head how to do this. So -1. So that makes it 0, taking the absolute value. So I'm basically just kind of flipping the definition of this, right? Here it was 1 if the driver was white, 0 if not. Here is 0 or 1 if the officer or the driver is non-white, and then 1 if they are. So I'm going to copy this, paste the values. So if I delete this, and you don't have to do any of that. I'm just going to show this to you, so don't worry too much about what I did there. So I've now got an identifier for was the officer white, was the driver non-white, and then the combination of those two was the officer white and the driver non-white. Okay, so I'm going to go to my data analysis. My Y variable, I'm going to choose to be whether or not they got a ticket. My X variable, I'm going to select all the way from the driver's, kind of if they're male, all the way over to officer's years of service, and include all of those. Okay. I selected the labels, new worksheet, I'm going to hit OK. Okay. So now that I have this output, right, let's look at, I want to go view real quick, zoom in. First of all, one thing we can kind of point out before we look at the results, I need to be very cautious about these results because my R squared is 0.03. I'm explaining 3% of the variation in whether or not someone gets a ticket. I should be very cautious of taking these results too far. There's still 97% approximately of the variation I can't explain. Okay, so with that in mind, we have these variables that we had before, but we now have these race identifier variables. So this is kind of interesting, right? If we look at kind of whether or not the driver is non-white, that's a 1 if they're non-white, 0 if they're white. So relative to being white, if the driver's non-white, holding constant these other factors, the increase in the probability of receiving a ticket is about 0.008, which if we want to convert that to a percent, 0.8%. Now, so we might say, wow, there's some evidence of discrimination going on. Now, if we look at the p-value though, right, it's relatively high. We can't say that with any level of significance that null hypothesis, right, we can't reject that. So we can't reject that, and I'll copy and paste this over just so we have it to look at. We can't really say that the relationship between the driver's race and getting a ticket is something other than 0, right? Because we can't reject the null. But what's interesting is if we look at the variable for, well, is the driver non-white, but also is the officer white? If that's the case, holding constant these other factors, so it'd be like saying 2 officers were the same years of service, at a pullover where the drivers are the same age, same gender, the drivers, the officers are kind of both white. Well, when the officer is white and the driver is non-white, that combination, the effect of whether or not a ticket is written increases by about 0.06. And the p-value is 0, so we can say that it's significant, right? So with 99% confidence even, the p-value this low, we could say that the combination of an officer being white and the driver being non-white increases the probability that a ticket is written, right? If I'm the mayor, if I'm the head of the police, this is a problem, right? This is evidence that potentially there's some discrimination going on, right? Now, obviously, 97% of the variation is left unexplained, so we're missing a lot of important things here. But this should be at the very least bit a little concerning. And definitely want to dive more into this to be able to understand whether or not this is being driven by important omitted variables or kind of why it looks like there might be evidence of discrimination going on here. Okay. Now, the interesting thing is we could do the exact same regression, but now I'm going to see, is there discrimination going on whether or not someone gets arrested? So I go to data analysis, hit my regression tool. I want the same X variables, but now my Y variable, I want to be this, were they arrested or not variable, right? I had my label selected, new worksheet, so I'll hit OK. Increase the view so you guys can see it easier. If I look at my R squared, well, it's even lower now. Right? I mean, this is, now I should be real cautious about these results. But the interesting thing is now when I look at this, right, if the officer's white and the driver's non-white, it looks like maybe there's a slight positive effect. Maybe it's more likely that that traffic pullover results in a arrest being made. However, if I look at the p-value, there's no way I can reject that null, which is that there's no relationship between kind of this race variable and whether or not someone's arrested. In fact, if I look at any of these racial kind of identifiers, the p-values are all very high when I'm looking at their effect or kind of their predicted power on whether or not someone's arrested. Right? So this is good. This is more comforting news, right? People aren't just being arrested because of the officer or the driver's race, but it doesn't alleviate the fact that it looks like maybe some tickets are being kind of non-proportionally issued to kind of non-white drivers when the officer is white. So I thought this was a really good example to kind of show the power of what we can do with some of this linear regression. It allowed us to think about making that rejection decision, interpreting these coefficients, thinking more about our R squared. And so I thought that was a pretty good example. Where were we? I think I'll save this for next class. I may also post a little a PDF of a small academic paper, so a peer-reviewed publication that we'll try to kind of walk through and do some interpretation on, just so we can kind of, like I said, see the power of this linear regression tool, understand just different contexts of making these interpretations, evaluating, looking at the p-values, looking at the R squared, and thinking about these things just more, just seeing different in context. So that's probably it for today. I said we'll be a little bit shorter. We'll do new content Wednesday and Friday. And as far as online quizzes go, from here on, I'm not going to do any online quizzes kind of post Thanksgiving. So all the online quizzes are over because I'm not supposed to kind of assume synchronicity. It's great if you guys can, but I'm not going to assume it. So no online quizzes kind of for the next 2 weeks. But I guess I will be posting those kind of fit Excel and Connect assignments. Like I said, depending on what you have from the previous 4, it's kind of up to you about whether or not you want to do those, since I do drop the lowest of each type. Any other questions from me before we kind of get going here? Otherwise, I'll be recording Wednesday, Friday, and Monday, Wednesday, Friday of next week at the same time. We'll go through some more examples, but also I can kind of approach it as office hours. If you guys do have questions on any of the homeworks, I'll kind of be available. Like even after, like right now, I ended it and you had questions, you we could work through some things maybe together. So, more questions? All right. We'll see you guys on Wednesday.